Dear student, in this lecture we will continue with the more about the solution of LPP. In previous lecture we have seen the graphical method and solution of graphical method and types of solution. They may be unique solution, unbounded solution, infinite solution or infeasible solution. In this lecture we'll learn the basic solution, basic variable and non-basic variable of linear programming problem. Now let us see the definition of basic solution. As we know that every linear programming problem is converted into standard form and LPP is written in the matrix form also. Therefore, we consider the system Ax equal to B be a system of linear equation with m linear equation and n unknown. Here n must be greater than m. And A is a matrix of order m by n. Let B is a submatrix of A, which is non-singular. We consider the submatrix of A, called it as a B. This is actually a small b, right hand side constant matrix small b. Then setting n minus m variable corresponding to the not associated with columns of B. We choose the submatrix of A and consider the n minus m variable which are not associated with columns of B are equal to 0, means we set these variables equal to 0 is called, and find the solution is called the basic solution. The m variable which are different from 0 are called basic variable, and the variables which we have set to be equal to 0 are called as a non-basic variable. It is called as a non-basic variable. And the matrix is called basis matrix, and x1, x2, xn are called the basis vector. As you know that if you have the equation something like as x1 plus x2 equal to 2 and x1 plus 2x2 equal to 4, then if there is equality, then you can call this equation as a algebraic equation. And if there are number of variables equal to number of equation, then you can also say that the given equation has a unique solution. But in LPP you have given the equation which are the constant is of less than or equal to type, greater than or equal to type, and we convert it. It may be equality type also, but if there is less than or equal to type and greater than or equal to type, you convert these equation, these constant into equality form by adding slack and surplus variable. What do you mean by slack and surplus variable? We have seen in the previous lecture. Now we move towards to the actually the basic solution. We have the equation is x1, objective function is maximize z equal to x1 plus x2 plus x3 subject to x1 plus 2x2 plus x3 less than or equal to 2, and x1 plus x2 plus 0.5 x3 less than or equal to 2. All x1, x2, x3 are greater than or equal to 0. We have to write the system in the form of Ax equal to B. Therefore, if this constant contain less than or equal to type, then you have to use the slack variable. Add the slack variable in both constraint, it becomes converted into standard form. See, the first constraint is x1 plus 2x2 plus x3. We add the slack variable, say x4 equal to 2. Another constraint is x1 plus 2x2 plus 0.5 x3. Another constraint is x1 plus 2x2 plus 0.5 x3. Here also constraint is of less than or equal to type. Therefore, we add a slack variable, say x5 equal to 2. All xi are greater than or equal to 0. Obviously, I is from 1 to 5. Then we write this as ax equal to b. Therefore, the system in the matrix form is A is a coefficient matrix 1, 2, 1, x4 is 1, x5 is 0. Second is 1, 2, 0.5, 0 and 1. x1, x2, x3, x4 and x5 equal to, the right hand side constants are 2 and 2. This is your system Ax equal to b. In the definition we say that write the submatrix of A, say capital B. We consider the submatrix, suppose 1, 1, 2, 2. Then determinant of B is equal to 2 minus 2, which is 0. But we have to consider a non-singular matrix. Therefore, we consider the another submatrix, say 1, 1, 1, 0. Anything you can consider, just check. If it is singular, then choose another matrix, submatrix. It is 0 minus 1, determinant of B is, which is equal to minus 1, which is not equal to 0. Therefore, B is a non-singular. Therefore, we can consider the submatrix of A as B. Then setting n minus m variable. Here your n is the number of variable is equal to 5 variables are there and number of constraints are 2, means n minus m, which is equal to 3. 5 minus 2 means you have to set the 3 variables are equal to 0. But which variable we have to set equal to 0? Which are not associated with columns of B. Here we consider the first column and 1, 2, 3, fourth column. Therefore, the remaining variables, say not associated with columns of B, means you don't set x1 and x4 equal to 0. Therefore, we have to set x2, x3 and x5 equal to 0. If x2, x3, x5 equal to 0, and then consider 1, 1, 1, 0 and our variables are x1 and x4 equal to 2, 2. Then solving these equation, x1 plus x4 equal to 2. Next is x1 equal to 2, because 1 into x1 is x1 plus 0 into x4 is 0. Therefore x1 equal to 2. If we put x1 equal to 2 in this equation, then we get x1 is equal to 2. Therefore we get here x2 is equal to 2 minus 2 is 0. Therefore our solution is x1 is 2, x2 is 0, and all variables which we have set equal to 0, that is x4, not x2, this is x4, x2, x3 and x5 are also 0. This is called the basic solution. And these variables x1 and x4 all are called basic variable, and x2, x3, x5 are called non-basic variable. Here x1 and x2 are basic variable, and 2, 3 and 5 are non-basic variable. And the matrix is called basis matrix. See, we consider another submatrix also. Let us see. This is your standard form of given LPP. We write into AX equal to B form, or we can take a B such that which is non-singular. Here we consider second and fourth column, and determinant of this also not equal to 0. Therefore this B is also non-singular. Now our M is 2, N is 5, number of unknown are 5, number of constant are 2. Therefore we set the 3 variables 5 minus 2, which is equal to 3. 3 variables are equal to 0. N minus M means 5 minus 2, which is equal to 3 variables. But which 3 variables? Second and fourth. Don't consider the second and fourth. Therefore which variable we have to set? x1, x3 and x5. We can consider another one also. See the submatrix, another submatrix 1, 1 and 1, 5 means x1 and x3. This is also a non-singular matrix. Therefore we set x2, x4 and x5 equal to 0, 3 variables, and consider these equation. Solving this system of equation, we get x1 equal to 2, x3 equal to 0. x1 is equal to 2, x3 equal to 0 is called basic solution. x1, x3 are basic variable, and x2, x4 and x5 which we have set to be equal to 0 are called non-basic variable, and B is called the basis matrix. Student, if you observe in previous solution, here we get the another solution. If we consider this matrix, then we get the another solution also. Means you can notice that there is no unique solution, but according to this, how we can conclude that this LPP has a degenerate solution? If your, please remember that if your basic variable is vanish, then it is called the degenerate solution. See, in this one, though I told that x1 and x4 are the basic variable, but x4 gives the value 0. Means what? Here x4 is vanish. Therefore you can conclude that this LPP has a degenerate solution. This one also contain the basic variable having value 0. See, x3 is equal to 0, It is a basic variable, but the variable is basic, but it vanish. Therefore, this solution is not unique solution. Next we see the another definition, next definition, basic feasible solution. If B is a basis matrix, then the basic solution choosing a submatrix of a system which can be written as xb equal to B inverse B. This B is a suffix. This is small b. Notation is x basic variable is equal to B inverse into B. In matrix theory, we learn about this already. If xb is equal to B inverse B, then xb are greater than or equal to 0, the basic solution is called basic feasible solution. If your solution means value of the variable are greater than or equal to 0, then our solution is called basic feasible solution. Degenerate solution. About the degenerate solution, I already explained. A basic solution of the system Ax equal to B is called degenerate if one or more basic variable is vanished. Here x3 is vanished. If we consider another submatrix, here x4 is vanished. Therefore, this solution is called degenerate solution because our basic variable is vanished. Now, let us move to the next method. We have already seen the graphical method, and graphical method is usually used for the LPP which contain only two variables, because we can easily draw the graph of the constraint, and if we consider the extreme point, we get the optimal solution. If your objective function is maximize type, it gives the maximum value. If your objective function is minimization type, it gives the minimization value. Now let us see the next method, which is a simplex method. It is very useful if your LPP contain more than two variable. Then we use the simplex method. If LPP, first step is, if LPP is minimization type, write it as a maximization type. Means if your LPP having the objective function is of minimization type, then we write it as a maximization type. Please remember that in our procedure we can't convert, actually we don't convert the minimization into maximization type. We ignore this step. If any, because there are so many reference book and this step is not mandatory, therefore we also ignore this step. If any one of the constant on RHS constraint is negative, multiply it by -1. As you know that if your constraint is of less than or equal to type or greater than or equal to type, we convert the given LPP in the standard form, and whenever you convert it into standard form, and if your right hand side constant is negative, then multiply the whole constraint by -1, then the right hand side constant is positive. Next step is write the LPP in a standard form by introducing slack and surplus variable. You already know about the slack and surplus variable. Then write the table as below. First column contains the basic variable x1 to xk, then admissible variable x1 to xn. Admissible variable means which you admitted into LPP while converting the given LPP into standard form. This is a right hand side constant. Then this is a -z, coefficient of z, but not coefficient of z, coefficient of -z. Means If it is C1 in objective function, write it as minus C1 minus C2 and so on minus Cn. Minus Z are greater than or equal to 0. Step number 5. Step number 5 is if all Cj are greater than or equal to 0, then solution is optimal, otherwise go to the next step. See, if this all Cj, all coefficients are greater than or equal to 0, then our solution is optimal. If any one constant is negative, then go to the next step. Find the minimum Cj less than 0. Means if your Cj is negative, then find the minimum of all negative. Then find the ratio xs, here notation is xs, minimum over bi upon ais. Bi means right hand side constant of that choosing variable and coefficient of variable in that column. AIS must be greater than 0. This is called the minimum ratio property. Next step is, here the variable xr where minimum is appear. If you find the minimum ratio over second row or second or third row, note by its suffix by xr. Here the variable xr will leave the basis and xs will entry in the basis. Means minimum Cj gives the entry variable and minimum ratio give the exit variable, and the element ARS is called a pivot element and or it is called as a key element. Then using the matrix, simple matrix transformation, convert the pivot element to the unity. You can convert, if it is unity, then don't convert or don't use any elementary transformation, elementary operation. Convert the pivot element as a unity by dividing its row by pivot element. Means if your element, pivot element is 2, then the divide that row by 2, it becomes 1, and all other elements in that column equal to 0. Means corresponding column elements are equal to 0 by using simple matrix transformation. Again check whether all Cj are greater than or equal to 0 or less than or equal to 0. If all Cj are greater than or equal to 0, then your solution is optimal. If Cj is less than, note that if Cj is less than or equal to 0 and corresponding element are also less than or equal to 0, means you can't find here the minimum ratio, because when you find the minimum ratio, AIS must be greater than 0. Then this indicates that the given LPP has an unbounded solution. We see one by one by solving some examples using simplex method. Means we find the we solve the LPP using simplex method having unique solution, having infinite solution, having unbounded solution. Let us see one by one. First example is, solve the following LPP by simplex method. Here maximize z equal to 3x1 plus 5x2 subject to 3x1 plus 2x2 less than or equal to 18, x1 less than or equal to 4, x2 is less than or equal to 6, x1 x2 greater than or equal to 0. 3 constant, both constant, 3 constant, all constant are less than or equal to type. Therefore, while converting the given LPP in the standard form, we use the slack variable. our objective function is maximize z equal to 3x1 plus 5x2 subject to first constraint is 3x1 plus 2x2 3x1 plus 2x2. We add a new variable x3 equal to 18. This is first constraint. x1 plus x4 equal to x2 plus x5 slack variable also equal to right hand side constants are 4 and 6. 4 and 6. This is the standard form of given LPP. All xi means greater than or equal to 0, means x1, x2, x3, x4, x5 all are equal to 0. Now you know that we convert, we first write the given LPP in the standard form, then by step number second says that if your right hand side constant is negative, then multiply by 1. There is no need to multiply the equation by -1 because all the constants on the RHS are positive. We using the slack and surplus variable, we convert the LPP in the standard form. Now we move to the step number 4. Write the table. First column is basic variable, second is admissible variable, then constant, then ratio if we need, x1 all admitted variable, x2, x3, x4 and x5. Our slack variables are first right here the slack or surplus variable. We use x3, x4 and x5. Write the coefficient matrix 3, 2, 1, 1, 0, 0 and right hand side constant is 2. 1, 0, 0, 1, 0. Right hand side constant is 2 and next is right hand side constant is 2 also. Next coefficient is 0, x2 is 1, 0, 0 and 1. Right hand side constant is 4 here and here is 6. Then here you have to write minus of z. your coefficient of C1 is 3 and 5. You have to write it as in terms of minus 3 minus 5. Then there is no x3, x4, x5 in objective function. You may consider here 0 or no need to consider the value. Our step number 5 is consider the minimum of Cj. Minimum is occur here, therefore your entry variable is goes in this direction, because in minus 3 and minus 5 is a minimum, therefore your entry variable in this direction is second number, means x2 is a entry variable. Then consider the minimum ratio. Minimum ratio is 2 upon 2. Right hand side constant is 2. And column element is 2, therefore it is equal to 1. 4 upon 0, don't consider that value, is a goes to infinity. And next one is 6 upon 1, therefore it is equal to 6. See, here we convert the LPP in the standard form. Instead of x1 there is a x2. I have already considered x2 na? 3 2 1 0 0 1 0 0 1 0 0 1 0 0 1. Right hand side constants are 18, 4 and 6. I consider it as a 2 by mistake. It is 18. Sorry, it is 18. Therefore 18 upon 2 is 9, and minimum ratio occur here 6. C. Minimum Cj is occur here minus 3 and minus 5, means minimum is here 5. 18 upon 2 is 9. 6 upon 18 upon this 2 is equal to 9. Right hand side constant is 6. I can't consider this element because 4 upon 0 goes to infinity. 6 upon 1 is 6, therefore minimum ratio is occur here. Therefore in this direction we get the pivot element. This is called the pivot element. 1 is our pivot element. See. You can bracket it. This is pivot element. Our procedure is that next step is that make the pivot element as a unity and corresponding column element as a 0. Means you have to make this element as 0. This is already 0 and this is also 0 by using the simple matrix transformation. Therefore the first row, operation on first row is R1 plus minus 2 times R2. Therefore 2 minus 2 is 0. Second row contain the 0 element, and last one fourth row R4 plus 5 times R3. Using this operation, you may say that this is basic variable first is, then next is admissible variable are as it is x1, x2, x3, x4, x5, right hand side constant. Then basic variables. Basic variables are here. You can observe that your x5 will leave the basis and x2 will enter under the basis. Therefore x3 is as it is, x3, x4 is as it is, but instead of x5 x2 will enter in the basis, therefore it is x2. In practice, it is easy task. First, the third row is coefficient of this one is 0, 1, 0, 0, 1. This row is as it is. R1 plus 2R2 minus 2R2. 3 minus 2 times R2 is 0. 2 minus 2 is 0. 1 minus 0 is 1. 0 minus 0 is 0. 0 minus 2 times means minus 2. 18 minus 12 is 6. This is already 0, then no need to do any operation. Write the row as it is. 1, 0 and right hand side constant is 4. Minus z. 5 times it is minus 3. 5 plus 5 is 0. Then 0 plus 0 is 0. 0 plus 0 is 0. 5 times means 5. And no need to do this operation, or you may do. Multiply this element by R4. 0 plus 5 means 30. Here the element is 30. Now minus 3 is a minimum. Again procedure is repeated because all Cj are not greater than or equal to 0. If you get the all Cj are greater than or equal to 0, then your solution is optimal. If it is not greater than or equal to 0, any constant is negative, then repeat the procedure. Repeat the process as first step is, this is a minus element, means only one element is minus, therefore in this direction x1 will enter in the basis. Now find the ratio. How to find ratio, you know. Consider the right hand side constant 6 upon element in that column, 6 upon 3 which is 2, 4 upon 1 which is 4, 0, this in this direction. Therefore you get this as a pivot element. Means convert the pivot element as a unity and corresponding element in that column are equal to 0, and x3 will leave the basis and x1 will enter into the basis C. See, this is minus 3 is the minimum. We consider the minimum ratio. 6 upon 3 is equal to 2. 4 upon 1 is equal to 4. Minimum ratio occur at here. Therefore, in this direction and this direction meet here. Therefore, this is your pivot element. Intersection of these one is the pivot element. Make the pivot element as a unity. Therefore, 1 by 3 R1 make do the matrix transformation of elementary operations are R1 upon 3 means 1 by 3 into R1. Next R2 minus 2 times R1. First you have to do this step first. Convert the pivot element as a unity. 1 by 3 R1. First operation is 1 by 3 into R1. Therefore it becomes basic variable are x1, x2, x4. Next 1 by 3, 1 by 3, 0, minus 2 by 3 and 6 by 3 is equal to 2. Then this element is equal to 0. After doing this, then use this row unit element while converting the corresponding column element equal to 0. Use this pivot element as a unity. Therefore R2, our operation are R2 minus R1. 1 minus 1 is 0, 0 minus 0 is 0, 0 minus 1 by 3 is minus 1 by 3, 0, 1 minus 0 is 1, then 0 minus 2 by 3 is plus 2 by 3, 4 minus 2 is 2. This contains the 0, then no need to do anything. Six, and last one is minus z is you have to do the operation. Minus 3 becomes equal to 0. Therefore do the operation R4 plus 3 times R1. Therefore this element become 0, 0 plus 0 multiply by 3, therefore it is 1, 0 multiply by 3, 5 minus 2, it is equal to 3, and multiply by 3, 6, and add, means it is 36. You can observe that all Cj are greater than or equal to 0, therefore your solution is optimal. See, and the solution is x1 is equal to 2, and the solution is x1 is equal to 2. See in this direction, x1 is 2, x2 is not x2, here is x4 na, x3, x4 and x2, x2 is 6. Solution is x1 is equal to 2 and x2 is equal to 6. Your objective function is maximize z equal to what is your objective function? 3x1 plus 5x2, 3 into x1, 3 into x1, 3 into x1 means 3 into 2 plus 5x2, 5 into 6 means it is 6 plus 5 into 6 is 30, which is 36, and 36. Here you already observe that this value is also 36. See, this is pivot element. Make this pivot element as a unity, and corresponding element are equal to 0. Therefore your x1 is 2, x1 is 2, x2 is 6, and our objective function maximize z equal to 3 into 2 plus 5 into 6, because it is 3x1 plus 5x2, which is 36. Now let us move to the next example. 3x1, this is also maximization type. 3x1 plus 2x2 subject to x1 plus x2 less than or equal to 4, x1 minus x2 less than or equal to 2, x1 x2 greater than or equal to 0. Both the constant are of less than or equal to type, therefore use the slack variable. Objective function is maximize z equal to 3x1 plus 2x2 subject to x1 plus x2, x1 minus x2, both the constant are less than or equal to type, therefore use slack variable x3 equal to x4 equal to right hand side constants are 4 and 2 and 2. All xi are greater than or equal to 0. I is from 1 to 3, 4. This is our standard form of given LPP. Our first step is the LPP is already in the maximization form. No right hand side constant is negative, therefore there is no need to multiply by -1. Then we convert the given LPP into standard form using slack or surplus variable. Here our LPP contains the both constant are of less than or equal to type, therefore we use only slack variable x3 and x4. Then write the table. Our table is, first column is basic variable, then admissible variable. I will write in short admissible a dot v, x1, x2, x3, x4. Right hand side constant. In first step, consider here as a slack variable or surplus variable, which are x3 and x4. The coefficient is 1, 1, 1, 0, 0. Right hand side constant is 4. Next is 1, minus 1, 0, 1. Right hand side constant is 2. Then minus z. Minus z is minus 3 and minus 2, 0, 0. Obviously here your all Cj are not greater than or equal to 0. All Cj are not greater than or equal to 0. Therefore we choose the entry and entry variable first, then by using the minimum ratio test we choose the exit variable. Here minus 3 and minus 2, minus 3 is a minimum, therefore here minus 3 is the entry variable. Therefore take the ratio first. Here is ratio 4 upon 1, which is equal to 4, then 2 upon 1, which is equal to 2. Therefore minimum ratio occur here, and in this direction this gives the pivot element. This is your pivot element. Our next step is make the pivot element as a unity. This is already 1, therefore we don't need to do this step, and make the corresponding column elements are equal to 0. Therefore, and first see the entry and exit variable. Here x1 is the entry variable and x4 is the exit variable. Therefore our table is as basic variable, admissible variable are x1, x2, x3, x4. Your x3 is as it is, but instead of x4 there is a entry variable is x1. Right hand side constant C. Then first write the pivot element row 1, minus 1, 0, 1, right hand side constant is 2. Then we will do the operation as a R2 minus R1. Therefore 1 minus 1 is 0, 1 minus minus 1 is 2, no R2, R1 minus R2. 1 minus 1 is 0, 1 minus minus 1 is 2, 1 minus 0 is 1, 0 minus minus 1, and 4 minus 2 is 2. Then next is Z minus Z. Here multiply the second row by 3 and add in the third row. The operation is R3 plus 3 R2. Therefore it is 0. Multiply by this equation by 3. It is minus 3, minus 2 and minus 3, it becomes minus 5. Then 0 plus 0 is 0. Multiply by 3 and add. Therefore it is 3. Multiply by 3 and add. Again minus, no all Cj are greater than or equal to 0. If your all Cj are greater than or equal to 0, then solution is optimal. But here no all Cj are greater than or equal to 0. Therefore minus 5 is the minimum. Again consider the ratio. Ratio is 2 upon 2 is 1. But we have seen in the procedure that AIS must be positive, but here it is a negative. Therefore we can't take the minimum ratio here, and there is only one element or one variable which will enter in the basis, that is x2 will enter and x3 will exit, and in this direction 2 is the pivot element. Again you know that the procedure is make the pivot element as a unity and corresponding column elements are equal to 0. Therefore first basic variables are x1, x2, x3, x4, right hand side constant. Here is x2 and x1. First divide the row, multiply the row by 1 by 2, means our operation is 1 by 2 into R1. Therefore it is 0, 1. Next element is 1 by 2 minus 1 by 2 and 2 by 2 is 1. Make this element as a unity. Therefore our operation is R1 R2 plus R1. Use this pivot element, then it is easy to do the procedure. 1 plus 0 is 1, minus 1 plus 1 is 0, 0 plus 1 by 2 is 1 by 2, 1 minus 1 by 2 is 1 by 2, and 2 plus 1 is 3. Then next is minus z. Multiply the element by 5 and add. Therefore the operation is R3 plus 5 times R1. 5 times means 0, 0. 5 times means it is equal to 5 by 2. 5 times means 3 minus 5 by 2. 3 minus 5 by 2. 6 minus 5 means 1 by 2. Then our constant is 6 here. R3 plus 5 times means 6 plus 5 is 11. Now all Cj are greater than or equal to 0. Therefore your solution is x1 equal to 3, x2 equal to 1. Solution is x1 equal to 3 and x2 equal to 1, and maximize z is becomes, our objective function is 3x1 plus 2x2. 3x1, 3 into x1 is 3 plus 2x2, 2 into 1, it is 9 plus 2 equal to 11. C. First step is -3 is minimum and 1 is the entry variable, and by using the minimum ratio x4 is a exit variable. Make the pivot element as a unity, which is already 1. Therefore there is no need to do any operation. Then make this element as 0 and this is 0. Therefore r1 r3 plus 3 r2 and r2 plus r1, no, r1 minus 3 r, see, 0 1 0 using the transformation. Then next -5 is the minimum. Again consider the minimum ratio. Negative element is here, therefore we can't take this minimum ratio. Again minimum ratio is 1. This is pivot element. Make the pivot element as a unity and corresponding column element as a 0. This is our here the last table is not occur. This is our last table. Therefore the solution is x1 is 3 and x2 is 1 and value is 9 plus 2 equal to 11. In the next lecture we will see the more examples on simplex method. Thank you.